Today we're going to take a look at what happens when we take the limit as x approaches the x value of a vertical asymptote in a rational function, and also as x approaches infinity or negative infinity in a polynomial or rational function. We already talked about the other day how if a function is continuous and we want to take the limit as x approaches a certain x value, we can just plug the value in. And this is true for most cases of rational functions, except when we are referring to the x value of a vertical asymptote, because in that case it is undefined, or if we are approaching infinity or negative infinity, because we can't actually plug in those values. So in those cases, we have to analyze the trends of the graph and take a look at where the graph is actually headed. Now, if we recap rational functions, things that we should remember are that they have horizontal and vertical asymptotes. For example, if I gave you the function 2x plus 3 over x minus 3, things that I would expect you to remember are that this function has a vertical asymptote at x equals 3, because that's where our denominator is undefined, and a horizontal asymptote at y equals 2, because that is the ratio of the x coefficients. Whenever the degree of the numerator and the denominator is the same, we just divide the coefficients of our x values. That being said, we can go ahead and draw a quick sketch. We know that we are going to have our vertical asymptote at x equals 3 and our horizontal asymptote at y equals 2. To complete my quick sketch, I would plug in x values on the left and on the right of my vertical asymptote. So I would evaluate f of 2 and f of 4. Plugging in 2 and 4, I get y values of negative 7 and 11. I can also find my y-intercept by plugging in 0 for x, and I get negative 1. If I plot each of these points on my graph, I will see that my function has points in these 3 locations. And that is enough information for me to see that my graph looks like this. Now, let me just be clear that drawing a graph is not necessary to be able to evaluate these limits. However, it is very useful because as we look at this graph, we can tell a couple things. Number one, if I were looking at the limit as x approached 3 for this function, I would know that it does not exist because from the left and from the right, we are approaching different areas. On the left, I approach negative infinity. On the right, I approach positive infinity. If I were looking at my limit as x approached affinity for this graph, I would look and see that as the graph extends off to the right, it is approaching my horizontal asymptote, so the value would be 2. And the same thing would be true for the limit as f of x as x approaches negative infinity. Our horizontal asymptotes tell us the trend of the graph as we extend onto infinity, and that's why knowing what these pictures look like can really be valuable as we are trying to evaluate these limits. When we are discussing our polynomials, polynomial graphs, if you recall, look all kinds of different. We can see things that look like this, we might see a graph that looks like this, or even something that looks like this. And we'll discuss those more in a minute. What I want you to keep in mind is if I were to take 1 and divide it by an extremely large number, for example, 1 divided by 1,000,000. If I were to do that, then this answer would be extremely close to 0. If I were to do 1 divided by a negative big number, this would also be very close to 0. It would just be approaching 0 from underneath. However, it is still approaching 0. Now, if I were to do 1 divided by a small number, for example, 1 divided by 0.00001, this is going to give me a very large number, close to infinity. And if I were to do 1 divided by a very small negative number, for example, 1 divided by negative 0.00001, then this would also give me a very large number, but in this case, it would be a very negative large number approaching negative infinity. In this section, we are going to analyze limits as the x value approaches the x value of the vertical asymptote. Now, when we are approaching our vertical asymptote, what we should remember is that our graph is either going to do something like this where they both go up. It might do something like this where one goes up, one goes down. Or it might do something where both parts of our graph go down. I find that drawing a sketch of our graph really helps. After we have drawn a graph or just begin analyzing x values around our vertical asymptote, what we want to do is determine if these values are going to be approaching infinity or negative infinity. And then lastly, as we analyze the overall limit, the answer will either be approaching infinity, negative infinity, or does not exist if we are trying to determine the limit as x approaches an x value, and on the left the branches approach one infinity, and on the right the branches approach the other infinity. In example 1, when I see this problem, I immediately know it's a rational function because I have a variable in the denominator. If I were to draw a quick sketch, I would know that I have a VA at x equals 0 and an HA at y equals 0. If I were to plug in x values on the left and right of this vertical asymptote, then I would see that my branches would be here and here, and I could draw in my graph to look like this. From this point, when I go to answer my questions, as I look when x approaches 0 from the left, I can see that this is the branch that is going down to negative infinity. So this would be negative infinity. As I approach 0 from the right, I am now skyrocketing up to positive infinity. And my overall limit does not exist because my branches are not both approaching the same value. Now if I look at my next example here, in this case, my vertical asymptote would be at 3/4, and my horizontal asymptote would also be at 0. Now you may be wondering, do I always have to draw a graph? No, you don't. In the cases of these simpler rational functions, just getting an idea as to where your vertical asymptote will be at can help you determine what values are good to plug in. So if I wanted to test an x value on the left and on the right, I would probably do f of 0 and f of 1. And that would tell me what the graph is doing as it is approaching the asymptote from the left and from the right. When I plug in 0, I get a y value of 1/3. When I plug in 1, I get a y value of -1. And so what that tells me is that my graph is going to look like this. And so now I can see as I approach my vertical asymptote from the left, I approach positive infinity. From the right, I approach negative infinity. And since I'm not approaching the same direction, in this case, my overall limit does not exist. In example 3, this problem is going to present a little differently since we have our denominator being squared. I can still find that my vertical asymptote is at x equals 2, horizontal asymptote is at y equals 0. Again, if I did a quick sketch, my graph would look like this. Values that I would want to plug in to analyze limit from the left and limit from the right would be f of 1 and f of 3. Now when I plug in 1, I end up getting 1 over -1 squared, which is just 1. And when I plug in 3, I get 1 over 1 squared, which is also 1. And so what I see in this case is that my two branches are both going to be above my horizontal asymptote. From the left, I approach infinity. From the right, I approach infinity. Therefore, my overall limit exists, and I approach infinity. Go ahead and try the last example on your own. Pause the video. In this last example, we notice that we have our horizontal asymptote is at y equals 1. This is because the degree of the x's is the same, therefore we divide those lead coefficients. Just as before, we graph our vertical asymptote at -3, and we pick x values on the left and on the right. Now those of you that may be against graphing and don't prefer graphing, notice that in each of these cases, what I did was I picked x values on the left and on the right of my vertical asymptote. And I used the answers to help determine which way my asymptote was approaching. So if you can use that information and draw the correct conclusion in terms of infinity or negative infinity, and you don't need to draw a graph, then that's fine. Drawing a graph is not required. I just find that it helps make it very clear whether or not we are approaching positive or negative infinity. When analyzing limits as x approaches infinity or negative infinity of a polynomial, now remember, a polynomial is not a fraction. We do not have x values in the denominator. So the problems that we see in example 5, those are all polynomials. When we are analyzing these limits as x approaches infinity or negative infinity, what we're really looking at is the idea of end behavior. And we talked about this last year in Algebra 2. We talked about how if our function had an even degree, such as x squared, x fourth, then both ends of the graph would be going the same way. If my graph had a positive lead coefficient, it would end up with an up-up, and if it had a negative lead coefficient, it would be down-down. Now if we have an odd degree, such as an x cubed, x to the fifth, then in this case my function goes in split directions. And if my a value is positive, then I go up to the right, down to the left. If my a value is negative, I go down to the right, up to the left. To help you remember these rules, just think about your basic linear line. Y equals mx plus b, and what a line with a positive or negative slope looks like. And in the even degree, think about your basic parabola and what it looks like if your a value is positive or negative. As we take these ideas and take a look at these next couple graphs, just do a quick drawing of your end behavior. So for example A, this is an odd degree, positive lead coefficient, so it's going to be up, down. For example B, this is an odd degree, positive lead coefficient, so again, it's still going to be down to the left, up to the right. Now, if we look at what limit we're taking, in example A, we are looking as x approaches positive infinity. Well, that would be this branch right here, which is pointing up, therefore my answer is infinity. If we look at part B, I'm looking as x approaches negative infinity, which would be this branch here, which is pointing down, therefore my answer is negative infinity. If I use the same idea to solve C and D, I can draw my end behavior graph. Since this is a negative a value in an odd degree, I will be up, down. And if I look at part D, positive a, even degree, up, up. Now in part C, I want as x goes to positive infinity, which is my right arrow, which is going down, therefore negative infinity. For the last problem, I want as I approach negative infinity, which is my left arrow, and is pointing up, therefore my answer is positive infinity. Now in part 3, we are going to look at limits as x approaches infinity or negative infinity in a rational function. Again, remember these rational functions are when we have fractions with x's in our denominator. If our rational function has a horizontal asymptote, and recall this occurs if the degree of the numerator is less than the denominator or if the degrees are equal, then what's going to happen is as x approaches infinity or negative infinity, the function value is going to approach the value of the HA. Now, in the case of where we have an oblique asymptote, and remember we have oblique asymptotes when the degree of the numerator is greater than the degree of the denominator. And an example of what that looks like, if you recall, that would be like maybe we had a dotted oblique asymptote and a dotted vertical asymptote. My graph would look something like this. And as you can see, as we extend off into positive or negative infinity, my graph is either going up to infinity or down to negative infinity, unlike with our horizontal asymptotes where our graph is leveling out. With our functions that have horizontal asymptotes, as I extend to positive or negative infinity, you can see how my graph just keeps on following the trend of that horizontal asymptote. So in the case of my oblique asymptote, what's going to happen is that f of x approaches infinity or negative infinity. So what you need to do is you need to analyze. This is going to take a little bit more work. You need to analyze the term with the highest power to see if the end result is positive or negative, leading us to positive infinity or negative infinity. So we'll get to that in just a minute. What we're going to do now is we're going to start with when the degree of the numerator is less than the degree of the denominator, or when the degrees are equal. All right, so if we look at example 6, here we see that my horizontal asymptote is going to be at y equals 0. Therefore, the limit as I approach positive infinity or negative infinity is automatically going to be 0. When I look at examples A and B down here at the bottom, in both of these cases, the lead term has a smaller degree in the numerator than it does in the denominator. So for all of these cases, my horizontal asymptote is at y equals 0. And the trend of these graphs as we extend to infinity is to pull towards that HA. So all three of these would have a limit as x approaches infinity or negative infinity equal to 0. In the case of our degrees of the numerators being equal, our horizontal asymptote is found by dividing our lead coefficients. And this is because if you were to plug in infinity, only the term with the highest exponent would matter. It has the most influence and it affects the answer the most. So if we look at example 7, again we're going to compare those degrees, and I would want you to notice that they both have an x squared degree. Their degrees are the same. So in this case, our horizontal asymptote is at negative 7/4, and that is what our limit will approach. When we look at part B, again, we see those degrees are equal. It does not matter if I'm approaching positive or negative infinity. Regardless, the limit will always equal the horizontal asymptote for that function. Now our last scenario is a little bit more complicated, and this is when the degree of the numerator is greater than the degree of the denominator. As we said, here we are going to see an oblique or a slanted asymptote. So what you want to do is you want to see, does the graph extend to positive infinity or negative infinity? And to figure this out, what we are going to do is we are going to pay attention to the term with the greatest degree. Again, it has the most influence. And what you are going to do is you are going to plug in a plus infinity or a minus infinity. And I know you're probably wondering, well, how in the world do I actually plug in infinity? You don't. What you do is you pay attention to, will the signs be positive or negative? Let me show you what I mean by that. If we look at example A, my two terms that have the highest power are 3x cubed and x squared. And I am plugging in a positive infinity. So basically, I'm thinking of this like, if I plugged a positive number in here and a positive number here, what would the outcome be? Well, 3 times a positive number cubed is positive, and a positive number squared is positive. Therefore, the outcome is also positive. And since the outcome is also positive, then that means that this limit is approaching positive infinity. If we do the same process for part B, we compare our lead terms, and this time I'm approaching negative infinity. If I were to plug a negative number into my numerator, a negative number cubed will stay negative. If I plug a negative number in and square it, it will turn positive. However, when I do a negative divided by a positive, the outcome is negative. Therefore, this limit approaches negative infinity. Go ahead and try the last couple ones on your own, parts C and D. In part C, we plug a negative into the x cubed, which will stay negative, and then we have a negative out front, which turns it into a positive. My denominator is positive, therefore the overall limit approaches positive infinity. Looking at part D, I have positive over negative, therefore I approach negative infinity. Now, in this last part, this one's a little sneaky. First of all, we can't really plug infinity in here, and we don't have exponents to fall back on. However, what I want you to remember is that our sine function has limitations. It is limited, and it is stuck in between -1 and 1, whereas infinity is ginormous. So even at its biggest, a value of 1, if I put that over infinity, 1 divided by something ginormous, whether it is a positive infinity or a negative infinity, is going to be so small it is essentially equal to 0. And this is going to be one of those limits that we just need to go ahead and either work through in that way or memorize. All right, that's it. Homework is worksheet 4.